sort of old problem. So what is this old problem? So we're going to situate ourselves in some very familiar examples. We'll have 4D abelian gauge theory. And A will be our gauge field, and F will be dA, the field strength. This is a dynamical gauge field. Sometimes I need to discuss background gauge fields, but this will be a dynamical gauge field. And we'll be concerned with a situation, which is quite common, where we have a classical U1 global symmetry. So I'll underline this word classical for emphasis. And J will be the current for this symmetry. Now, it's classically conserved, so there's an equation like D of star J equals 0. This just means that J is conserved. But as we learn in kind of the first course in quantum field theory, in general, J is not conserved at the quantum level. This is the subject of the so-called Adler-Bell-Jackiw anomaly. So often you find an equation that is D star J is some integer over 8 pi squared. Actually, maybe I don't want to call this K. I'll just call this 1 for now. Times F wedge F. So this is the so-called ABJ anomaly. The term anomaly in physics has become wildly overloaded, but this is the oldest, so we have to respect it. So this is true in a zillion examples. Let me just jog your memory about some of them. So kind of the easiest one that you can latch on to, it's just massless QED. So we have Weyl fermions, chi plus and chi minus. These are Weyls. And their gauge charge is plus and minus 1, according to this superscript up here. And we could take J to be a chiral symmetry. So, for instance, chi plus rotates to e to the I theta chi plus, and chi minus is inert. So this is a chiral symmetry, and this is kind of the first example that we learn where classically the current is conserved, and quantum mechanically one has this ABJ anomaly equation. So this chiral symmetry is what gives this talk its name, this non-invertible chiral symmetry. We'll soon learn what the adjectives non-invertible are supposed to mean. Let me just highlight another simple example to latch on to. That's axion electrodynamics. So in that class of examples, one has a periodic scalar field theta. It's periodic, so it's identified with itself with some periodicity. We'll call it 2 pi mu. This mu is sometimes called the axion decay constant. This is a periodic scalar field. And to say it's an axion means that in the action, one has a term like I over 8 pi squared mu integral of theta F wedge F. And you could take J in this problem to be the axion shift symmetry. So then this interaction here will induce this equation for that axion shift symmetry. Okay, so those are some really basic examples of this. Of course, there's like discrete analogs. You can generalize this in lots of ways. but we're going to focus on this class of examples and this kind of anomaly. And let me highlight here some puzzles and questions. So this anomaly and its implications is kind of like a tortured history. And the reason is that it's a bit paradoxical. So what's the basic question? The basic question is, does J generate a conserved charge? Are there conserved charges? Are there selection rules, etc.? Do we organize states into representations? So, the kind of conventional path to learning about this is you say, well, classically, yes, quantum mechanically, no. And so, maybe one answer you would say is emphatically no. At the quantum level, J is not conserved. And maybe you put a full stop there and you stop thinking about this problem. But actually, there's a subtlety here. The subtlety, as far as I'm aware, was first sort of really cleanly remarked upon by 't Hooft. So maybe a smarter answer is yes. Why would you answer yes? The reason is that the conservation is violated by abelian instantons. So this is 't Hooft. What do I mean by that? Well, suppose you want to generate a net violation to the charge conservation in some infinite time process, like in an S matrix calculation. Well, then you would need the integral of f wedge f over all of space-time to be not zero. This is needed to violate. But if you're a simple person on, say, S4, which is usually what we think of as like a regulated R4, there are no abelian instantons.
Hi, Clay, but there are configurations that carry non-zero f wedge f, right?
In the functional integral?
Yes.
On S4? Yeah. No, not without more sophisticated insertions.
So just topologically, f wedge f is zero for every configuration on S4?
Pointwise, f is not zero, but on S4 topologically, the integral of f wedge f is zero.
I see. Okay, thank you.
Yeah.
So, Clay, is it important that you are working with the abelian gauge theory here?
Yes, it is essential. It is essential. If I were talking about the non-abelian gauge theory, then this f wedge f would here have been replaced by trace f wedge f, and then there are non-abelian instantons on the 4 sphere.
Right. Okay.
So that integral would really not be zero, and then the answer no would definitely be correct.
And why is it that only the integral matters and not the pointwise value?
Well, what I'm imagining is, suppose you want to derive something like a selection rule. So I have my S4, and or you could think it's R4, and I'm trying to see if, like, in the far past and in the far future, the charge agrees.
But on S4, it will automatically agree because all far past and far future is the same point.
So well, okay. So
on the other side, require S4.
On S4, the question is, if you insert local operators and compute the correlation functions, do the selection rules on those correlation functions implied by the existence of this charge, are they actually correct? And the fact that S4 doesn't have sufficient topology to activate the integral of f wedge f actually means that the answer is yes. those selection rules hold for local operator correlation functions.
I see. I see. I see. So you're saying the local operator correlation functions on S4 always satisfy the selection rule.
Yeah.
Okay. Thank you.
Clay, and T4 clearly it can be violated, right?
On T4, it can be violated. So Shiraz, this puzzle about the topology is actually part of the resolution that I'm going to come to. So,
Okay.
like what we want to do is, so it's clear that there's a dependence on the topology of space-time, right? As Shiraz is kind of pointing out, what you need to get non-zero integral of f wedge f is you need some kind of two cycle. You need a two-dimensional subspace that f can wrap, some kind of magnetic flux. And that will kind of be key to figuring out what is the way to think about this situation more intrinsically.
And also,
Okay.
sorry, maybe this is something you will say, but in the cases where it is a selection rule, presumably one can think of some sort of a 't Hooft anomaly involving this guy and the other two, or any other flavor symmetry that you may have. And is it matched across the RG flow? So
Well,
this is a bit tangential.
So we have this puzzle, and a kind of related puzzle is what's intrinsically significant about J? How do we intrinsically say what's going on here?
Yeah.
So we would like to say that this situation that we've described here encodes some notion of symmetry. And once we have that kind of abstractly defined, then we can think about the kind of question that you raised, Abhijit, like, does it match along RG flows? Does it have anomalies? Does it match across dualities, et cetera? It's every kind of thing that you would take in the bread and butter situation you would like to put this into. But first we need a way, a kind of intrinsic definition of what's going on, intrinsic point of view on what's going on here.
So, sorry, Clay, I'm going to ask what's probably a very stupid question. Say we had a forebrain. This instanton kind of charge, f wedge f charge, is zero brane charge on that forebrain.
Yeah.
So if I just had one single forebrain going off to infinity, are you saying that cannot carry zero brane charge? Its field configurations cannot carry zero brane charge?
Well, I think what you're highlighting, no, Shiraz, what you're highlighting is that there's an interesting UV sensitivity here, which I was attempting to mask, but you're bringing up, which is like point-like instantons are some kind of UV sensitive object that are sort of outside the universe of U1 connections. Let me put it that way. That's not a great answer, but
I see. But you're saying the only configurations that carry this charge are singular configurations.
yes,
There isn't a more smooth thing that would shrink to the singular configuration.
that's correct. Yeah.
Okay, thank you.
Yeah.
I have a question.
Yeah.
So this issue of that Abhijit was raising of whether one should look at the integral of the f wedge f, whether that vanishes or the f wedge f directly vanishes, whether that is important, is resolved by the fact that when you're looking at the charge, it's the integral over the J0, right? So when you're looking at whether the charge itself is conserved, you have to look at the integral over the f wedge f over the entire space. Is that correct?
Yes. This is correct, but Abhijit is still raising a valid question here, which, or maybe let me just unpack something, which is that here I wrote integral over all space-time.
Yeah, that's it. But I think it should be integral over all space instead of all space-time.
No. All this is not. This is like Q dot, if you like. What I'm writing here is, Q dot. Well, let me not write it, but the Q of t equals infinity minus Q of t equals minus infinity is equal to this expression that I wrote. So I'm writing like long time change. I'm not trying to write the charge right now. I was trying to write what you would need to have happen to have the net violation of the charge.
Okay, then it's overall space-time. I agree.
Okay, so this we'll be able to get at these puzzles. One clue here to focus on is that this is going back to this question of what's intrinsically significant about J. is that F, the thing that appears on the right-hand side of the divergence of J, this F wedge F, is not a generic operator. It satisfies an equation, which is that dF is equal to 0. Most operators don't satisfy any differential equations. This operator satisfies a differential equation. And an important point is that this means that in kind of the modern language, this F generates a symmetry. It's a kind of higher current. So it generates a one-form symmetry. What that means, just to jog your memory, is that the charged objects are lines. In this case, they are 't Hooft lines. So when we write the abelian ABJ anomaly equation, divergence of J is F wedge F. The thing that is this is a kind of intrinsic equation because it involves currents on all sides. And that's somehow the key thing that's going to eventually enable us to say abstractly what we're talking about here. Okay, so our basic idea, let me go to a new page. So the basic idea of what I'll do is I always like to use that to define the chiral symmetry non-perturbatively. So I will argue that there is a notion of symmetry here that is analogous to other notions of symmetry, but there will be a price that we will have to pay, a price of this ABJ anomaly. And that price will be that this chiral symmetry becomes what is called non-invertible. And rather than explain to you what that means in the abstract way, I will show you in the context of the construction. So hang on to your hats if you're uncomfortable with this word non-invertible. Okay.
I have a small naive question. When you're dealing with QED, usually dF is star J, right? So it's not 0. Isn't that correct?
dF is star J. No, d star F is J. So the Maxwell equation is that d of star F is J electric, and d of F, if you like, would be J magnetic, but we don't introduce any magnetic charges, so dF would just be 0. Okay, so let's unpack what it would mean to define this chiral symmetry non-perturbatively. What are we trying to do? So what are we trying to do technically? So in QFT, there's a nice language for symmetry. The symmetry we could think of as a kind of topological operator. We're going to use this dictionary. So this is, if you like, kind of Noether's theorem extrapolated to the max. So, for example, if we don't have the anomaly, without this problematic divergence, what do? So we write the exponential of I alpha integral over some 3 manifold of star of J. So J is a 1 form, star of it is a 3 form. We could integrate it over a 3 manifold, and this generates the symmetry. Let's draw a picture. So the picture is that you have some 3 manifold. It's codimension 1 in space-time. So this is some M3. This is where we put this operator here. We've put it on this M3. And, you know, it's topological, means that if you can wiggle M3 around and nothing will change in the correlation functions. Except sometimes when you do such a wiggle, you may cross a local operator. If you do that, you pay a price because of the ward identity. So it looks the same. You have your M3 again. But now here you get back your local operator dressed by the phase that comes from the action of this symmetry on this operator. So this is our topological operator. Right, I mean, if we think of M3 as a spatial slice, then this is just the finite transformation of the integral of J0, the exponentiated integral of J0. So here I'm just situating that in a Euclidean framework. So that's what we want to mean by symmetry in quantum field theory. And so then you could say our goal technically is we want to define a topological operator, define, construct, discover something, topological operator associated to the anomalous J, the ABJ anomalous J. So that's what I'm going to try to do. So any questions about this?
So is the understanding that when you kind of try to commute the surface across from O, you kind of encircle O by a very small surface that picks up the phase, and then you kind of detach the rest of it and
yes,
take it.
that's the right picture. The right picture is sort of pull off a S3 blob of M3 and surround O. And then, you know, the cost of shrinking that 3 sphere onto O is this phase. And then the rest stays the same.
Okay, thanks.
Yeah. These kind of word identities are also quite natural. People sometimes write very similar things in conformal field theory. Yeah, go ahead with the next question.
Yeah, just to clarify that this phase, it's just a phase that you're picking up because the symmetry is abelian. Is that right?
Yes. Here I'm just doing the abelian case. More generally, you would have a representation of the, you know, some other operator in it. It would be the action into multiplets.
Okay, cool. Thanks.
Okay, just a naive question. In the presence of this anomaly, why couldn't I do something very naive, which is to, you know, say that f wedge f is d of something?
I'm about to do this naive thing, Ankar.
Oh, okay, sorry.
I'm about to do this naive thing and tell you sort of what's wrong with it.
Okay,
like.
okay, thank you.
And then sort of go from there. Yeah,
great, thank you.
But so that's a great that's a great lead-in. So a kind of naive attempt, which you can even read confusing things about in Weinberg. I think people started doing this sort of immediately after the anomaly was discovered. As you say, well, look, f wedge f, if I squint, is just is d of a wedge f. So what I mean by that is I can write down star j minus 1 over 8 pi squared a wedge dA, and this is now closed, or its Hodge dual is conserved. So you could say, well, forget you with this funny d star j is f wedge f. I'll just write down this modified current, and you could ask, does this make sense? So I'll just integrate over M3, this thing that we just discovered, star j minus 1 over 8 pi squared a wedge dA. So does this make sense? Well, you've solved the divergence problem, but you've paid a very kind of gross price, which is that this is formally topological, but it's definitely not gauge invariant. So this is not gauge invariant. So we don't like that solution. That's not really correct. And you could try to pin, but it's close. And somehow the next step didn't really occur to people for some number of decades. Maybe it wasn't that important. And but we could try to pin down what makes it not gauge invariant. If I go back to this, this slide here, so obviously J is gauge invariant, so this integral is fine. The problem is this one. We have I alpha over 8 pi squared A wedge dA. Now this is almost like a Chern-Simons term. A wedge dA is the kind of natural thing we could think of as a Chern-Simons term, but we have a very unusual coefficient. We have alpha over 8 pi squared. So we could try to interpret it in terms of a Chern-Simons level. The Chern-Simons level, if you would, is alpha over 2 pi. And this is not properly quantized. So, so that's sort of the root of the non-gauge invariance problem, okay, the gauge non-invariance problem. Okay, so what to do? So one thing you could say is, well, I know how to quantize the Chern-Simons level. We could say, well, if alpha over 2 pi, this level was an integer, that would be allowed. And indeed it is allowed, but it is unfortunately sadly trivial. This is like doing a 2 pi rotation in U1. So this is like kind of the nothing transformation to take alpha over 2 pi to be an integer. Because alpha was the angle by which we were trying to do this rotation. Okay. Now there's something else we can do, and this will be non-trivial. So we can try a fractional level. So we can try alpha equals 2 pi over k, where k is an integer. So it's like the level is 1 over k. So this is a fractional level. And those of you who have studied three-dimensional gauge theory before might anticipate where I'm going. I'm going to necessarily get into some kind of fractional Hall physics now. So that will be kind of the main trick here. So how can we make sense of a fractional level, a fractional Chern-Simons level? Well, it doesn't make sense on its own, but a fractional level, it does make sense as a response. So what do I mean by that? So let me consider a partition function of a three-dimensional theory. It will depend on a variable little a. Little a is our gauge field of the bulk, but it will be fixed in this discussion. I'll write integral dc. C will be a 3D U1 gauge field. So I'm going to write a three-dimensional functional integral. So here I write exponential of ik over 4 pi integral c wedge dc. This is a standard well-quantized Chern-Simons term for c. K here is an integer. It's the same k that we had up here. So nothing fractional there. And then I just couple this c to my a. So this is a totally well-defined functional integral. And if you naively complete the square, this is just equal, if you like, to the following. So when is this expression, what do I mean by this equation, that this partition function is equal to this phase? What I mean is that if you're on a very simple manifold for your quantum field theory, like S3, for instance, and you don't insert any Wilson lines of this dynamical gauge field C, then this partition function is equal to this phase. More generally, though, the partition function of this U1 Chern-Simons theory, this level K Chern-Simons theory, is not equal to a phase. And more generally, we also don't know how to define this quantity here. So they agree when this one is defined. So what am I going to do? So first of all, are there questions about this technical statement? It's kind of the key technical statement.
Sorry, I didn't quite understand this comment about Wilson lines, absence of Wilson lines allowing you to define this.
What I mean, Abhijit, is that suppose you literally take this partition function,
Yes.
on where the three manifold that you're doing the integral over is S3.
Mm-hmm.
Then the answer is this phase.
Mm.
That's what I mean. So that's just a technically true statement. And so somehow what that means is that this is kind of what you might try to mean by fractional level.
Right. And when is not true? You commented on when this is not true also.
Right. So it's not true if the three manifold that you do the functional integral on is more interesting. It's also not true if instead of just the naked partition function, I start inserting Wilson lines of C, non-trivial operators. And relatedly, when I try to put this on a general three manifold, this expression does not make sense, just does not compute. Because it's an ill-quantized Chern-Simons term. So the main thing is that when this expression is well defined, it agrees with this.
I see. Okay, thank you.
More questions?
Average dA.
Yeah.
You're saying that, I mean, in general, this integral is defined over a three manifold, right?
This is defined over some three manifold, yes.
Yeah. So
this will
in general, when you talk about Chern-Simons theory on three manifolds, they are not usually gauge invariant. That's what you're saying. I mean,
they're not gauge invariant unless the coefficient is chosen to be appropriate. So here the coefficient is okay. So usually the coefficient has to be an integer divided by 4 pi.
Okay.
And that's why this is sort of not well defined, generally speaking, because the coefficient is not of that form. The issue is just that A is a gauge field. It's not really a one form, right?
Yeah.
So because of that difference, you have to pay the price that you have to put a special coefficient there.
And I was just wondering, when you consider non-abelian gauge fields, for instance, non-abelian Chern-Simons,
yes,
wouldn't average dA when augmented by the average A term make it gauge invariant?
No, it's the same thing. The same issue occurs. You still need a very specific coefficient in order to make that well defined.
Okay.
It's not well defined for general coefficients. It's only well defined for certain quantized coefficients.
Okay.
Clay, just to understand, if just to see if I'm understanding this, is the point that Z of A, as you've defined it here, is better defined than the naive A Chern-Simons term with the fractional coefficient, fractional level, but it has the same gauge transformation properties under a transformation of A. So you could instead use this to define your. Is this the point?
This is exactly what I'm about to do.
Okay.
Yes,
Thank you.
That's exactly the point.
Thank you.
Right. So Z of A is completely well defined, but it has all the same, as Ankar said, it has all the same transformation properties. So now we're going to make a new well-defined. So we're going to construct. Okay, this is completely illegible. Well, okay, maybe I should also say that this expression here, this is like the this is this 1 over K. This is the we're coupling. What are we doing more abstractly? We're coupling U1 level K. Sorry, I keep messing up my writing here. U1 level K to dA, which is F, through the one form symmetry. This one form symmetry generated by F that I highlighted previously. And this is the same kind of coupling that occurs in the fractional Hall effect. So, okay, with that aside, we can now write down this well-defined operator.
Sorry, is there a reason why we should think of this dA as a one-form symmetry rather than just the field strength of the gauge field?
Well, from the point of view of the three-dimensional theory, A is frozen. From the point of view of this three-dimensional theory, A is just some frozen background. And I'm telling you what I'm doing is that this U1 level K Chern-Simons theory has a one-form symmetry. And so I can naturally couple it to anything that has a gauge field for this one-form symmetry.
Okay. Okay, fine. Yes, thank you.
Yeah. So that's like kind of the symmetry way of thinking about this coupling that I'm doing.
Okay.
So, okay, we're going to make a well-defined operator, topological operator, not for all alphas, but for, to start, just for alpha is equal to 2 pi over k, this fractional rotation. We can call this dk. It lives on M3. And, okay, what is it? Well, it's defined to be this piece times z of a. And as Ankar correctly observed, this z of a is well defined, but has the same all the same gauge transformation properties as this kind of phase that we wrote down in the naive prescription.
And this is well defined on any manifold, right?
This is well defined on any manifold. Yes. This is a topological operator that is well defined on any three manifold. So it's a bona fide symmetry, but it's going to be slightly unusual because of the kind of meat of the construction here. And so now what I would like to tell you about is sort of what are the usual but also unusual features of it. Okay, so let's give some comments. Okay, so when does it work? It works for actually any rational angle. Alpha is 2 pi q, where q is a rational number. I did it just for q is 1 over k, but you can do it for any rational, but not for continuous alpha. So there's actually nothing, because there's no continuous generator here, there's nothing, so far as I currently understand, that resembles a conserved current. There's not really quite an infinitesimal version of this. There's finite chiral rotations by rational angles.
And as you change your angle, you're adding sort of a angle by angle, you're adding a different new dynamic degree of.
Yes, exactly. I'm adding a fractional Hall state that I need to get that Q. It's a complicated thing that I'm adding there for different Qs. So it's clearly, you know, essential feature here is the anomaly. So it's widely applicable. It's not particular to any specific construction. Whenever you have this anomaly, this abelian ABJ anomaly, you can run this construction. And so as a result, this gives an intrinsic definition.
ABJ anomalies always comes with a one form symmetry.
The abelian one does.
Abelian
kind
one.
of
Okay.
Right. The abelian one is where the divergence of J is F wedge F, where F is a generator of a one form symmetry.
Sorry, by abelian one, you mean what do you mean?
I could say it intrinsically. So we have D star J is when I write F wedge F, you might say, if I'm not in a gauge theory, what do I mean by F? I think this might be your question. But F here is a two-form current. So it has an intrinsic meaning already. That was F, remember that dF was 0. Yes. So F is an operator that we could identify just by knowing the symmetries.
Right. Okay.
So that was the point of saying that this equation, we can see what it means just using symmetries. For the non-abelian case, we have no hope of this.
Sorry, but what do you mean by the left-hand side is a non-abelian? Which I mean the global.
If I change this to trace f wedge f,
yeah,
then
right.
this doesn't factorize anymore. This is just a generic scalar operator now.
Yes, yes.
Right,
That's
but now this operator is not generic. It's a product of two currents.
Yes.
It's that difference that I'm using.
Yes. Okay. Thank you.
Okay.
Think of the trace f wedge f as sum over fi wedge fi over I.
But none of those are gauge invariant. None of the individual FIs are gauge invariant in that expression. Okay. Right? The F that appears here is really a well-defined gauge invariant local operator, which satisfies a kind of conservation equation. By contrast, if I change it to the non-abelian case, I get trace f wedge f, and there's no way to split that apart into smaller, simpler pieces in a gauge invariant way.
Okay.
Okay, so this gives an intrinsic definition of the abelian ABJ anomaly, where I've now explained what I mean by that. And now we can, as Abhijit suggested, now that we know kind of abstractly what we're talking about, we can use this as a symmetry in kind of the way we might like to use other symmetries. We can track it along our G-flows. We could try to discuss anomalies. We could see what it means for it to be broken by a little bit, all those kind of things. Okay, but those are some kind of beating our chest comments, but so let's talk about some technical features. So, okay, this acts on local operators in the standard way. That's the first thing.
Sorry, and Clay, just to check, you could do everything you've done here, you could do for a T4 as well, right?
Yes. This doesn't depend on the topology of space-time. This works in any manifold.
Right, but on a T4, the original symmetry was violated.
Yes, I'm coming to that right now. Yeah. So it acts on local operators as a chiral rotation, meaning that, so I mean, it's blind to this TQFT. Acting on local operators as a chiral rotation, meaning if I put this defect, this one with alpha is equal to 2 pi q here, if I put it on an S3, a little S3 inside any ambient manifold, and here's my O, then this is just equal to this phase I alpha QO times O. So it satisfies that kind of ward identity. But now we see we're going to pay the price for the ABJ anomaly. So it acts very unusually on 't Hooft lines. So remember, 't Hooft lines are world lines of magnetic charge. They're the electromagnetic dual of Wilson lines. So, you know, what's that thing? You have a line in space-time, and surrounding this line is a two-sphere. And on this linking two-sphere, the integral of F over 2 pi is equal to m, the magnetic charge. And the essential point is that this creates the topology needed to violate for abelian instantons.
Sorry, I have a question.
Yeah.
So when you magnetic charges, you no longer have df equals 0, right?
These are operators. These are not fluctuating magnetic charges. So you know, the lower dimensional anomaly analogy would be: imagine you have a standard conserved charge, but you insert a charged operator. Well, then you know that the ward identity says that the current is not conserved. It has a contact term where it touches the other operator. That's basically this picture again, up here. that's the same thing for the one form symmetry. DF is not 0. It has some contact term support along this line. But it's just a contact term. It's just an operator. It's just a number, not an operator.
It's not defined all over space, that you're saying. It's confined. It has support on a single line.
It has support on a single line, and moreover, in this discussion, the line is an operator that you get to, whose position you get to fix. The line isn't fluctuating. This is a line operator. It's a something I can insert into correlation functions.
Okay.
Okay, so this is supposed to help with Shiraz's question. So first, let me tell you, how does it act on 't Hooft lines? It acts weirdly on them. It's a feature, not a bug, though. So again, we'll draw our little diagram. So here will be our dk or dq of M3. Well, let me call it D. Let me do the K case. It's easier. And here's my little 't Hooft loop. And now I try to do the same thing and pass this this M3 through this loop. And what I find is something very interesting. I find that this line ceases to be a line per se. It becomes an open surface. So we have this open surface here that ends on this topological operator. And what is this surface exactly? It's the exponential of I over k integral f over 2 pi over this surface. So this is the surface S here, and this is the same S. So what this means is that this Wilson line, when it tried to sneak through this, this symmetry operator, it acquired a fractional electric charge. You can think of this as a kind of version of the Witten effect. So this is, if you like, a kind of higher version of the order-disorder map in Kramers-Wanier duality. So I remind you, in Kramers-Wanier duality in the Ising model, Kramers-Wanier duality is a little bit unusual because it maps order, it maps order to disorder, so it maps local operators to semi-local operators. Here we have a similar thing. This is mapping loop operators to loops with surfaces attached. Okay, so now let me say one other property, and then maybe I'll talk a little bit about, I'll talk for a moment about selection rules. So this symmetry is non-invertible. What does that mean, that word that people use, non-invertible? It just means that it has no general inverse.
Sorry, Clay, why is this phase like acquiring a fractional electric charge?
Well, it's because I told you what the surface is. So this surface is the integral, what lives on this surface is the integral of this f.
Mm-hmm.
If you tried to say f is dA, let's just integrate a over the boundary using Stokes' theorem. Then it's like on this line, the thing that was the line, you have an electric charge 1 over k.
I see. I see.
So you got dressed with a topological surface, which is this topological surface operator that is actually related to the one form symmetry.
Got it. Yes.
Okay, so there's no general inverse. That's what we.
And sorry, what happens if you try to move now the defects through this surface, through this extended surface on the right?
If I tried to move what? Sorry.
So if you move the 't Hooft loop through the surface, you got this like extended object, right? And now if I try to move it.
So this is a 3 manifold. I'm just bad at drawing. This is a 3 manifold. This is a 1 manifold. This is still a 3 manifold. This is a 2 manifold, and this is down here is a 1 manifold.
Right. So now I was just wondering what happens if I try to move this defect operator again through the through the surface S on the right.
You're asking how does it act on S's? Well, I mean, if
Yeah.
I could move it back through and it will undo it.
So it does undo it. I mean, I was just wondering if that's part of the non-invertibility in the.
Yeah, well, I'm going to write, so let me write an equation which is maybe kind of related to what you're asking. So when people say a symmetry is non-invertible, what they mean is that there's no general inverse operator. So there's a variety of ways to characterize that, but kind of the most intuitive is to just go back here and look at this, this definition that we gave, where we said that the symmetry is this thing that looks like the exponent, the thing that wants to be sort of the naive symmetry, times a partition function. And the reason this is not invertible, if you like, is because this partition function is very rich. I've put some degrees of freedom now on the defect. I've put this Chern-Simons gauge field there. And what it means is like, for certain three manifolds, this partition function could just be 0. So for instance, this partition function being 0, of course, then this dk has no inverse. So, kind of the there's an algebraic way to characterize non-invertible symmetries, but maybe the more kind of intuitive way is to say that the symmetry is non-invertible if it's a topological operator on which a non-trivial topological field theory resides. And that's what we have going on here. Now, if we try to characterize it algebraically, we could try to construct the inverse. The inverse, we would try to CPT conjugate the defect, try to write something like the fusion rule of D with D dagger. So we take dk of M3 and we try to collide it with dk dagger or dk bar, whatever notation you would want to use of M3. And what you get, yeah.
Another point. So when you have, say, D of F, the right-hand side is not exactly 0. Forget whether it's defined on some submanifold or something like that. But if it's not exactly 0, then how do you define the charge which generates the one-form symmetry? I mean, the charge in.
I think you should try to answer this. Try to answer this question for. So let's remember that if we have a standard symmetry with a standard current. So normally you say the current is conserved. So forget ABJ anomalies. So let's just have a little lesson about Ward identities. So, but the divergence is not in general 0 in the presence of charged operators. So if I put O of 0 here, this has some delta function times O times the charge.
That's correct.
Right. So what that means is that in the presence of other operator insertions, the current is not conserved. There's a Ward identity. The exact same equation is true with more indices for F in the presence of a magnetic charge.
No, but this holds only when the divergence of the current is 0 in the absence of any other thing.
Yeah, and that's the case. That's the case for the example that I'm talking about.
Is it? Because for your case,
there's no dynamical magnetic charges. The divergence of the current is only contact terms. As correlation functions that are only contact terms.
The divergence of the current is 0.
So DF is 0 away from magnetic charge insertions.
I mean, could you write an analogous expression of the previous sentence for this case?
Yes, I guess so. I could try. It's there'll be some delta function supported on the line. It will be. I mean, I'll have to write.
Yeah, perhaps it's best maybe if we let Clay proceed. So
Yeah, let me
maybe get in touch with Clay later about this.
Yeah. Let me just finish with this. So the thing I wanted to tell you was about the algebraic way to characterize non-invertibility. So the algebraic way to characterize non-invertibility is to try to construct the dagger of the operator. The dagger just means sort of conjugate with CPT, and then try to fuse it with the original thing. So if, usually this would be this is a unitary operator. So you would think that for a usual symmetry, you'd say that this fused with its dagger should just give you 1. more generally, unitarity implies that for any operator, you should get a fusion channel that contains one, but not necessarily equal to one. So what do we actually get? So here we get a sum over surfaces S in H2 of this manifold with some coefficients that, okay, that's for the cognoscenti. And then we get an exponential of I over 2 pi k integral over this surface of S. So this is what's called a condensation defect. So here we have a sum over all the surfaces. We're kind of summing over magnetic charge that's in this, that's inside this M3. And okay, there's one channel here. Think of this as a fusion equation, analogous to fusion equations that you might encounter in Chern-Simons theory, right? So when you collide various different lines. So there's one channel in here where S is equal to 0. When S is equal to 0, this is just 1. So that's the identity channel. That's the statement that D times D dagger contains 1. But it also contains all this other stuff. And the point is that this other stuff means that there's no operator that we could fuse dk with to get 1 exactly. So algebraically, this is not like a group. There's no general inverse operator. Its fusion is richer. And the analogy to keep in mind is like the fusion equations in for lines in Chern-Simons theory, where you have line A and line B, and they fuse to some NABC sum over C's, line C. That's a fusion algebra, but it's not a group in general. Here we have something similar. Okay, so I guess I've just about finished my time, but maybe let me say something about selection rules. So good. So what do I want to say about selection rules? So how to derive selection rules in general and see what the rule is on. Yeah. Go ahead.
Let me just say that you're free to take some more time if you need.
Okay. Well, there's one, since there were some questions from Shiraz about what's the difference, what's going on T4, excuse me, versus S4. How does that work? Now that we have this operator, this dk, sort of all questions can be answered uniformly.
One question. Question. So the identity on the right hand side is the one corresponding to the trivial element of H2. Is that what you said?
Yes. Yes, exactly.
I see. Yeah, please go ahead.
Yeah. So now we have this operator. So suppose you want to derive selection rules. What do? So you take some, say, big S4. Let's start with S4. And okay, maybe we have some local operators inserted. How do you derive a selection rule? Well, you nucleate a little bubble of this symmetry defect up here near the North Pole. It's a topological operator, so nucleating it around in a tiny sphere with trivial topology doesn't cost you anything. So here you put dk of M3. This M3 is actually equal to S3 in this discussion. And now we try to move it down. Whenever we cross a local operator, it surrounds it, it acts, and then we try to close it off at the other side. So we get that this is equal to some phases here. Times the same thing, where now, let's see, maybe make sure I get all the same operators. Let's see, I have 1, 2, 3, 4, 5, and now I'm down here with my dk of M3, dk of S3 down here. And now I close it up on the other side. That's a standard way to derive selection rules. But now you can try to understand what would happen, for instance, if I enriched this correlate. So this would give you the standard chiral symmetry selection rules on local operator correlators. You could try to understand what happens if I insert.
One question.
Yeah.
The standard case, is this selection rule telling me that all the charges need to sum to 0?
Yes.
What does so the fact that I can only work with rational angles, that must lose me something.
Well, if you can do any rational angle and the charges are quantized in some units, I think he doesn't lose you anything.
Okay.
If you can really do any rational, Okay, so what I was going to say is, imagine we enrich this situation by considering a more general class of correlation function. For instance, we could have some kind of line here, some 't Hooft line. Now when we cross, so this is our 't Hooft line. Now when we cross, we get this more interesting symmetry action. So this thing becomes, say, a surface, filled in surface. This is the surface. So now you see that in the presence of the 't Hooft line, it's not necessarily the case that the charge is summed to 0. Instead, you learn that the correlation function with the line and the other operators inserted is equal to a phase times the correlation function with this surface operator inserted. That's the kind of selection rule that you derive. You can play this same game, Shiraz, on T4, for instance, where you try to cut open a small bubble and move it around. And now the topology will prevent you from closing it off on the other side. So you'll derive kind of correct results, but they won't say that correlation functions vanish. They'll just be relations among correlation functions.
So those will have integrals of f over various classes of H2 insert.
Yes.
Various elements of H2 inserted. Is that what will happen on the right side?
Yeah. So here, for instance, this open line, this line here became an open surface. And on that surface, I have this integral of f over 2 pi times I over k. So that's the sense in which I've derived a selection rule, but it's one that relates a correlation function with a line to a correlation function with a surface. But the charges need not sum to 0 in this sector. So it tells you what the right selection rule is there.
Right. And suppose I was an experimentalist interested only in correlation functions of my operators without this additional sector that you've put in.
Without the line?
Yeah, with the line, but without this additional topological field theory that you've added. I just want to know what I can say about what selection rule I can get for the correlation functions of the operators of my original theory.
But the 't Hooft line is an operator in the original theory.
Okay, with that line then, but without adding in some. I see. So this, you say your final answer does not depend on the addition of that topological field theory.
This is intrinsic to the theory, right? Yeah. So I killed DK on the other side. Yeah.
Okay. Now I understand. Thank you. Yeah.
So just to make sure, Clay, I understand this tracking. So let's say you have a 4 manifold with more interesting second homology, and then as you nucleate it at one point, this defect, and then go and shrink it on the other side. In between, you will get insertions of these integral f's on various.
So let me say that I think it's clearer to think using a state operator correspondence, Abhijit. So it's clearer to think that, at least to me, so a general 4 manifold with 2 cycles, you could think that those 2 cycles just mean that you have a 't Hooft line somewhere, right? Like a 't Hooft line just is the surgery thing that you need to glue in to create 2 cycles in your manifold with non-trivial f on them. So you can replace, in other words, you can replace a complicated 4 manifold by a network of 't Hooft lines. Same thing.
Okay, this would take some time to digest. There are constructions of 4 manifolds that are like that, but I wonder whether it's exactly that, because there are two ingredients usually that are usually in these constructions.
Well, maybe I'm talking about like a simply connect. Okay.
Maybe the simply connected ones go like this. I don't know.
So okay. But indeed, so I mean, you can apply this rule on any 4 manifold. So you have it's just that you know, depending on the 4 manifold, you may not be able to shrink the decay on the other side. There might not be a notion of other side. You might just end up with, that you can move it from one place to the other at the cost of doing these manipulations on the other insertions.
Yeah. And if you apply this to T4, then you will just recover the original ABJ anomaly equation, right? You'll get violation is related to F wedge F.
Yes, but F wedge F is summed over.
Yes, right. So, okay, fine. I understand. Thank you.
Right, exactly.
Yeah, so this is the advantage. One of the advantages I would say of having this topological operators. It sort of makes the notion of trying to figure out what's going on in different topologies with different insertions just completely algorithmic. You just insert this thing and move it around and see whatever you derive is what you derive.
Right. Okay.
Thank you.
Yeah. Okay. So let me now stop here and take any more questions. So thanks very much.
Okay.
Any questions?
One question, Clay, the one that I asked in the beginning of the talk. So with this, now that you have a nice symmetry with nice selection rules, can one play these Tooft anomaly matching games with this global symmetry?
You can, though it's very, very fresh to even say what the Tooft anomaly is. Pavel Putrov has some very recent work on this, saying what the anomaly is, but I don't think it's yet been used. So it's just, the answer is definitely yes. It's just, kind of too recent.
I see. But would you expect just it to be, I mean, so here, you work hard to make a well-defined symmetry, but is it at the end of the day, you just take that global current and consider some global type of anomaly as if you forget the global gauge anomaly and just match it in the IR. I ask this because, it's basically what you lose is somehow real to rationals and it doesn't seem to matter that much. Is it at the end of the day your expectation that that's what should match?
I'm not sure, to be honest.
Okay.
I mean, a related situation that kind of pragmatically occurs. So I gave you sort of the easiest setup where you have the U1 and you get a full rationals, but this also happens with discrete symmetries very commonly. And that situation has also a lot of some interesting dynamical applications, but there it's harder to say what you're going to get.
And you expect that such an ABJ anomaly in the context of non-abelian gauge theory just cannot be fixed, right? From the point of view.
I think it cannot be fixed, right? Like the selection, there's no hint that there's any selection rules. Like the selection rules, even with local operator insertions, removing all lines, they're just violated.
Yeah. Okay.
Yeah, and sorry, Clay, I think you said this, but just to confirm, the big difference between having, let's say, some set of Topf lines and being on the torus is that the Topf lines have fixed flux, whereas on the torus you get to choose what flux you put. So sort of, if you've got a particular network of Topf lines, just from the ABJ anomaly equation, you know by how much your conservation is violated. Is this right? Whereas on the torus, it's some summed thing.
It's a sum of things, yeah.
So you have, in some sense, much less information on the torus, whereas fixed Topf lines, you sort of know your selection rule is violated by a fixed amount.
Yeah.
Okay, thank you.
Okay, if there are no more questions, let's thank the speaker again.
That was fantastic, Clay.
Yeah.
That was fantastic.
Great talk, Clay.
It must be the fifth talk I've heard on non-invertible symmetries, and the first, it's certainly the first one I've understood.
Okay, yeah, I mean, I think non-invertible is a not a great name. It just means that something lives on the symmetry defect.
Yeah. It was so clear. Thank you so much. It was so beautiful and simple.
Thanks a lot,
Okay.
Clay.
Great talk.
Wonderful talk.
Hey guys,
Bye.
always a pleasure. Talk to you soon. Bye.